All right, so this is Math Stat 341 probability. So what I want to do is I want to continue going through the material of the semester by talking about applications. And so we're going to do two different applications today. So the first is MonteCarlo integration. And then the second is initially not going to look like it has anything to do with probability. It's the EggDrop problem. It's one of the most enjoyable problems I know of mathematics. Have you seen this one? Yes.
Yeah.
How many eggs have you done it with? Okay, so it's not the one you're thinking. Okay, so it's a great problem. There's a lot of wonderful mathematics behind it. And then we're going to look at it in a certain way that will bring in probability, and hopefully you will see the connections to the world around us. So some general items is we're going to be discussing a lot of issues with optimization. So there are ways to do calculations, but frequently the ways are just computationally impractical. If I want to determine if a number is prime, well, one thing I can do is I can check all the numbers less than it and see if anything goes into it. That's expensive. Even if I know that you only have to check up to square root, it's still so expensive, it's not practical for the size of the primes you need for modern day encryption. So you want to find ways to do things quickly. A lot of this is going to come down to dynamic decisions where you don't have a hard, fast rule where you actually adjust a little bit based on the data that's coming in. And as you go further in statistics, you can start to think about how this is going to affect the inferences you make, that you don't have a hard and fast, but you're willing to adjust based on where things are. How many of you have done differential equations, a class on differential equations? All right. If you had done a class on differential equations, you might have seen something about how do you numerically solve a differential equation. If the derivative is close to zero, what does that mean about the function? Relatively stable. And if the second derivative is also close to zero, what does that mean? Yeah, it'll be even more stable because there's no acceleration. So if you only have finitely many data points where you can evaluate things at, if the first and the second derivative are both small, there's really not that much change going on. And you can approximate it extremely well. You want to look for places where the function is changing rapidly, and you might want to do more observations there. So you're adjusting things dynamically. The next is the choice of metric. We've talked a little bit about this before. Depending on how you choose to evaluate something, you can come up with very different definitions of what is the right or the best answer. And we saw this, for example, in the method of least squares. Depending on what metric you choose, you can get different best fit coefficients for the line. Okay, so what I want to do is I want to talk a little bit about MonteCarlo integration. And the way MonteCarlo integration works is the following. So you start off with a large box of area A, choose endpoints, and see what fraction are in your set. And basically, the fraction that is in your set times the area of A should be an estimate for the area. So the area of omega should be approximately the number of n in A divided by n times the area of A. When we were in the old building, which was running down a little bit, I actually brought in the dartboard for people to throw dots. Given that this is our first year in the new building, this is not the time to be throwing dots at the building. If people want to throw dots during reading period, I'm happy to bring down the dartboard. Okay, so we'll spend time and I'll provide snacks. So here is the first couple of points. Blue are the points that are not in the region, red are the points that are in the region. Can you tell me what the region is from this? Right? And this is one of the dangers. I threw a bunch of points at random, and I'm choosing my points uniformly in a square that's 2 by 2. What do you see when you look at how these points fall? What's annoying? We're missing this huge area to here. We just don't have any observations. So because we have no observations at all in that area, I have no idea what's going on. Do you have any thoughts about what's going on in terms of looking at the red and the blue as to where my region is? Yeah, excluding the big unknowns. We have a big unknown in through here. And exactly how far this unknown is also unknown. Yeah, so maybe something like this is like the red area, and maybe something like this, like the blue area, something like that. Anybody want to guess maybe what the shape might be? Ellipse. So ellipse is actually correct. It's a very special ellipse. Circle. Okay. So one of the problems is when you're choosing the points uniformly at random, you could actually have large regions where you just don't get any data. What could you do to make it better so that you don't have this problem? So one is to increase n. And as you just take more and more points, the likelihood that you have some points in here becomes very, very high. And with high likelihood, you'll have a good uniform sampling. It turns out, and this is the big lie of Calc 2, and I'm somewhat excited that I'm finally going to be teaching Calc 2 in the spring after going 20 years without ever teaching it. We give people the feeling that they can integrate when they leave the class. They can't, I can't, no one can. We have to work really hard to come up with functions that we can integrate in closed form. Most integrals have to be done numerically. Now, there's lots of techniques. You've seen Riemann sums. If you had a good calculus class, you might have seen Simpson's rule, which is a little bit better in terms of estimating the area under curves. This is another way to try to estimate values of integrals. This is extremely valuable if you're looking at, say, your 300 plus dimensional space, and integrals like this do arise in finance. And so if anybody's interested in careers like that, let me know. Have a lot of Williams students who would be very happy to talk to, former Williams students who'd be very happy to talk to current Williams students. How do you evaluate a 300 dimensional integral? Well, if you have a region where you can tell very easily, am I in the region or not, then this technique is beautiful. You don't need to be able to evaluate the function precisely. You just need to be able to tell, am I in the region or not? Am I, say, between two curves or in some region? Switching to some numerics. Okay. Shift now. Numerics. Okay, so I'm going to play this slowly. Hopefully it will work pretty well. And it's going to add more and more points, and you can see it's filling in. Yeah, I don't know why it stopped. I'll speed it up. All right, so you can see the points getting added. And now, for some reason, it's lightening it up. It didn't do that in previous years, but it's lightening it up now. You can see that there are definitely large gaps. And so there are issues with choosing points like this. But at this point, you can see it's doing a very good job of estimating the region. Anybody want to guess what that number is above? Sorry? It's not pi, but it's the estimate for the area, right? And so pi is about 3.0905 today. There's a little bit of a slip in the market, okay? This is not bad. It's not perfect, but you were looking at 8,000 data points. So throwing in 8,000 dots, you were getting, I even went for up by 0.05. Oh, yes.
Yeah, like I feel like it's really nice to like
well, so I look at what fraction of the points lie in the region, and then I multiply by the area of the box. So the area of the box here is 4. So I would be multiplying by 4 in this case. So the question is, how accurate do you think something like this is going to be? we want to get a sense of, let's go back. We want to get a sense of how accurate we are. So we have, space here. Here's our set omega. Here's A. And we take endpoints, IIDRV observations. Say x1, x2, ... xn. And let's let x be their sum. Xk takes on two values. 1, if x is in omega. 0, if x is not in omega. What's the probability we take on the value of 1? Yeah, so note xk is 1 with probability area of omega over area A, 0 otherwise. What kind of random variables are these? Again, this is a review of the semester. Not Poisson, not binomial. Bernoulli, right? Bernoulli. What is their sum? Sum is binomial. Bernoulli. Sum is binomial. What's the expected value of x? That's just n times the expected value of xk, right? Which is just n times the area of omega over the area of A. Yes. Which is good, right? And so if we wanted to estimate the area estimate is the expected value of x divided by n, which is the area of omega over the area of A, the relative area, right? Because this gives us the expected number of points that are in our set omega. That's when we divide by n, that's going to give us the fraction. What's the variance of x? So what's the variance of the sum? The sum of the variances because it's independent. And we have n of them, so the variance is going to be n times the variance of x1. Right. And so if we call this thing over here p, this is going to be n p1 minus p. And so if we look at not the expected value of x, but if you look at, let's say, y equals x divided by n, then the expected value of y is just the area of omega over the area of A, and the expected, I'm sorry, not the expected, and then the variance of y is the variance of x divided by what? So we divide x by n. So if you multiply a random variable by 5, what do you do to its variance? By 5 squared. Right. The standard deviation is unchanged. So the variance of y would be the variance of x over n squared. So this would become p1 minus p over n. So it means the standard deviation is going to be of size 1 over square root of it. So in terms of our estimation of how good something is, it means the error is roughly like 1 over square root of n. Right, that's not bad. So it's converging like 1 over square root of n. So anybody want to tell me roughly what the square root of 8,000 is? No. Square root of 8,000 is not 0. 8,000. What's a number close to 8,000 that we like? So you can go to 10,000 and the square root of 10,000 is 100. You can go to 8,100, square root of that is 90. So the square root of 8,000 is roughly, 90, give or take. So we have P1 minus P. And so if we have our circle, we want to try to estimate this. Where is P1 minus P going to be largest? What value of P? Half. So if you plot this, when P equals 0 or 1, you get 0. It's a parabola that goes like this because it's got a negative term. So the greatest uncertainty is when P equals a half. But that makes sense. The greatest uncertainty is going to be when your region is half the total space. You have an equal chance of being in or out. So we would expect our error in estimating the area of the circle to be roughly 1 over 100, up to a little bit. All right, so 3.09 is not so bad. It's ballpark what we would expect from something like this. As again, this is a really simple argument. It uses a lot of the concepts we've done all semester. Sums of independent random variables, looking at the expected value of a sum, looking at the variance of a sum, looking at very nice ones like Bernoulli, trying to get a sense of what is the correct scale to study the problem. The correct scale to study the problem is going to basically be like 1 over square root of n for the uncertainty. So if we take n equals 10, that could be a sizable error. But all the way up to 1,000, 10,000, that should be enough to give us a ballpark estimate of what's going on. Now the danger, as we saw earlier, is that when we start doing a small number of points, we might be missing something. So rather than choosing the points randomly from a uniform distribution, what might you try to do? So you could try using a lattice. And so, maybe, I have my square inside here. And maybe what I do is I choose, a bunch of points like this. And so on. Dot, dot, dot for the dot, dot, dots. Okay. What is the problem about choosing a lattice? So, I'm always going to have gaps, but if the lattice is very large, it should be very nice and uniform. It's a really subtle issue as to what is difficult about using a lattice. So we're thinking of a square lattice, right? How many dots am I throwing? What can you tell me about the number of dots I must be throwing? It has to be a perfect square. So imagine you have a certain amount of time to act. So years ago, I was working on a project where I don't even know if this will make sense to any of you. In the old days, you actually read these things called newspapers, and they would tell you what time movies were playing. And people would look at them to figure out when a movie was happening. And if anybody is watching the TV show Ghosts, one of the characters on it, died in the 1980s, and he was a travel agent. And he just doesn't understand how can people, well, what happens if your plane is canceled? Well, you just call. Well, and just, the technology has completely changed. So you would have to read a newspaper and find out when the movie is playing because you wouldn't go online. So the movie theaters got the list of movies, and within 2 hours of when they got them, they had to come up with schedules. And so I was working with some people to help optimize the schedule. It's a really nice combination of a lot of different applied math subjects. And so the question was, what's the best schedule we can come up with, given that we have a little bit less than 2 hours to run, because we have to then give them the prediction. So you let the program run as long as you can, and then you do the best that you have at that point. So over here, if we want to work on a lattice, maybe we have a lattice that's 100 by 100 that gives us 10,000 data points, but things ran a little bit better than expected, and we can let it run for a little bit longer. How do you put in those extra points now? You know, you would love to go up to, instead of a lattice of 100 by 100, maybe 105 by 105, but you've already put in these points. You can't just easily adjust the lattice size. So if you have extra time, if you're doing a dynamic, if you're doing a fixed structure like this, you can't take into account the fact that now you have the ability to run it a little bit longer. What you could do is you could then maybe put in a smaller lattice in between, or you could just have those other points just be chosen uniformly at random, so you can do something with it, but you would much rather do a larger lattice. So what you can do is you can use special types of quasi-lattices, and the Fibonacci numbers are related to this. And so I've included some links about stuff like this if anybody's interested in reading a little bit more, because the Fibonacci numbers are irrational. And so we talked a little bit about this when we were doing Benford's law, that if you have an irrational number beta, then n times beta mod 1, the fractional parts, are uniformly distributed. So you can basically use this, you can use the Fibonacci numbers to create basically, to create things that are coming up like this, and then they'll just keep wrapping around. So that just as you get more points, it just keeps filling things in. And then if you actually have a little bit more runtime, it's not a problem at all. So there's a lot of ways to improve the simple things that we're doing. So we'll shift to code again. And so hopefully you can very quickly see the ellipse converging. And so this is an ellipse inside the square 2 by 2. Anybody want to guess what the area of the ellipse is? So it looks like it goes from -½ to ½, -1 to 1. So 1/2 pi. So what's nice is this is giving you a conjecture. So we want a formula for an ellipse in general. Well, we can do Monte Carlo simulations. We can change some of the A and B, either the semi-major and the semi-minor axes, and try to get some data and try to make a conjecture. If the semi-major and the semi-minor axes are the same length, what kind of object does the ellipse become? Circle. So we know whatever formula we have must reduce to the formula of a circle when they're the same. So just using our guess, and this is a way to review a little bit from multivariable calculus. So using our guess, so here's -a, -b, b. So what are we guessing the area is? Pi AB. And it reduces to pi r squared if A equals B equals M. So just from looking at some Monte Carlo simulations, we actually got a guess. One way to prove this, so we have x over A squared plus y over B squared equals 1. So what we want to do is we want to integrate over the ellipse 1 dx dy. Okay. If we change variables, we can make the ellipse into a circle. Let's let u equal x over a, b equals y over b. And so now we have an integral over a circle. what does the function 1 look like when we change it from xy to uv? Function 1 is still 1. We have to figure out how does dx dy change. Well, if u equals dx over a, we get du equals dx over a, dv equals dy over b. So dx dy is going to be ab du dv. And there you go, it's I, because it's a unit circle. So a nice way to just quickly review some of the results of multi-group calculus. Okay, so what I want to do for the last part is I want to do the EggDrop problem. Okay, it is all it is cracked up to be. So this is an extremely absurd situation. Okay, you have a building and you want to know what is the highest floor you can drop an egg off the building without the egg breaking. And you have very special eggs. The eggs never suffer any cumulative damage below being completely destroyed. So either the egg is completely destroyed when it lands, or there's no damage at all. You can drop it as many times as you want below the critical floor. Yes. Doesn't matter. Because if there is, you can just incorporate that into what happens. And so there is some critical floor. From this floor on up, it will break. And below this, no damage. And we have n floors. What do you think the goal is? Fine. So we want to find what floor. So imagine you have one egg and you want to find what is the highest floor that you can drop it from without it breaking. What would you do? Yep. Start bottom. Is there anything else you can do? No. Imagine you have two eggs. Well, if you start at the top,
We have break it one time, figure out where they stop.
the problem is if you start at the top and it breaks, it gives you very little information.
Yeah, but then you
Okay,
just
wait.
keep going down.
Yeah. One at a time. Okay. So one possibility is start in middle. So if you start in the middle, if it doesn't break, wonderful, you've eliminated half the possibilities. This is a binary search. So this was the marriage problem, where you sample a little bit, and then after a while, you take the first one that's better. So here, this is closer to binary search. Did we talk about Newton's method and divide and conquer? So this is like the divide and conquer. You start in the middle. If it doesn't break, wonderful, you've eliminated half the possibilities. What if it breaks?
Then you start.
So if it breaks, what do you have to do now? So start from the bottom. So the problem is, as soon as it breaks, the only thing you can do is one at a time. So when it breaks, you're then in trouble.
So the higher you bet your first egg, the more your first egg.
Good. So the higher you start, you have a lot of possible gain, but you now have a lot of risk. So one of the things we could be interested in is trying to figure out what is the minimum number of drops we need to determine the floor where it breaks. And then depending on the distribution of what floor is likely to be the critical floor where it breaks, that could adjust your strategy. For instance, if you believe that it's very unlikely it's going to break on one of the low floors, then you might be a little bit more willing to take a risk. And this is where the probability starts coming into play. Depending on what you know, this is the risk-reward system. When you are building an elevator or you're building a bridge, what's your big fear? It breaks, right? And so the advantage of having a little bit extra weight or a little bit extra traffic has to be balanced with just how catastrophic it would be if it completely breaks and you lose everything. And so you err on one side. So over here, what is the metric we're going to use? We could use what is the least number of drops we need in the worst case scenario. So whatever strategy we come up with, imagine the floor is the worst possible choice for us, given that strategy. We could say, well, you know what? I don't want to live my life thinking about the worst case scenario. I want to look at my expected value. And I want to choose a strategy that gives me the best average number of drops needed. But I might fail a couple of times. And if you think about some of the policy decisions being made, for instance, on the pandemic, a lot of these calculations, that's exactly what's going on, is trying to weigh what is best for society on average versus how catastrophically bad would it be if we made a mistake. The probability book I used when I was a college student had a problem about, is it worthwhile for humanity to build a missile defense to protect us from a dinosaur killer asteroid? And basically, it estimated what the cost of the system would be, and it tried to estimate how much the continued existence of humanity was worth. And it was an interesting calculation. And according to the authors, it wasn't worth protecting humanity. That it was much better to just gamble that for 50 years, no dinosaur killer comes, and then the cost becomes much more affordable to build a protection system. So over here, if we drop it in the middle, what's the worst case? Okay, so worst case, it's one drop, and now we have basically n over 2 to do. So it's basically like 1 plus n over 2 total. Okay. Yes.
Okay.
So the worst case would be roughly n over 2 drops. So one extreme was we dropped it in the middle. What's the other extreme? So what's the complementary extreme case? Again, this is one of the reasons I love this problem, is talking about thinking about extreme cases. Well, no, but I mean, saying you have to give me another place where it drops. So how many floors up should I go for the other extreme case? Well, if I go all the way up, I have a huge window, right? So the problem here is that if I start in the middle, if it doesn't break, I've eliminated half the possibilities. If it breaks, I now have to check half the possibilities one at a time. All right, what did the Patriots do this past weekend, which was pretty extreme in the NFL? Only 3 passes for the New England Patriots. And so it was almost entirely a running game. So what is the opposite? So here we did it in the middle. And so if it failed, we had to check a huge number, we had to check it over 2. So what's the other extreme where if it fails, we have very little to check? How many up should we go for the first drop? Well, if we do a quarter,
3 floors.
but then that's still going to give you a large number to check.
Second floor.
Second floor. Second floor is the other extreme. So one possibility was start in the middle. The second is go up 2 floors. So now if it breaks, you only have to do one more check. That's the complementary analysis. Yes.
That is the egg. First floor, like the egg always is gonna survive.
Nope, it could break on the first floor. So if you go up 2 floors and it breaks, then you have to check the first floor. So in this case, you do it every 2. So I could check 2, 4, 8, 10, 12. I could check all the way up to n, not 6. Oh, no, sorry, it's Spaceballs where they skipped 7, not 6. So I could check 2, 4, 6, 8, 10, 12, all the way up to n. And then as soon as it breaks, I have one more to check. So the worst case here is basically n over 2 plus 1 total. So what's interesting is these 2 cases are basically complementing each other. In the first case, we eliminate a huge number every time it doesn't break. But if it breaks, then we have a lot to check. In the other, we eliminate very little on each time, but as soon as it breaks, we almost precisely know where it is. We know it's within one. So what do we want to do? So we want to find the idea. We want to meet in the middle. So meet in the middle. Go up. So now we want some function of n floors. So let's say we go up x floors. So the worst case is we go x, 2x, 3x, 4x, all the way up to n. So we could have n over x times before the first egg breaks. And then for the next one, how many could it take? Once it breaks, we know within how many floors must it be. Because we're going up x every single time. X minus 1. And these maybe have a minus 1. I don't care. I'm just trying to get the rough idea of what's going on. So we now have basically n over x plus x. We did the extreme when x equals n halves, and we did the extreme when x equals 2. So did x equals n halves, x equals 2. Let's look at the function. I don't want to use f because we're using it before. Let's look at the function g of x is n over x plus x. Where is this smallest? How do we find where this is smallest? So good, we don't need the endpoint, so I don't have to crash into the board. So one is take the derivative. So we get g prime of x is negative n over x squared plus 1. Critical point is x equals square root of n. So that's one solution. That's one way to get the solution. Another approach, let's equalize. Try n over x equals x, which gives x equals square root of n. I am not saying that this gives the best. I'm just saying I have two competing factors. One factor is this n over x term, and one is this x term. I want both of them to be small. Well, if I make n over x small, I'm making x large. If I make x small, I'm making n over x large. So one possibility is, well, why don't I set the two bad things equal to each other? And if I set the two bad things equal to each other, that gives me x equals square root of n. This may not give you precisely the best answer, but it should give you something that's reasonably close. Because I want each term to be roughly as bad as the others. So, if you know calculus, which we should, because that's a prerequisite, you've taken 3 calculus classes to get here, we can just use calculus. And it tells us that if we take square root of n, that's the best thing we can do. It turns out this is not quite the best answer, because you can move by unequal amounts. And so, for instance, if when you drop the first egg, if it doesn't break, then now it's like you restarted the game with a smaller thing. So if first egg doesn't break, starting new game, right, with n minus x floors. It's like the memoryless hoops game. Not quite. This is the best I can do to try to review the hoops game, and probability again. The goal is to try to choose things that pull everything together. So what you would probably want to do is have that first drop a little bit higher. Because again, when we're looking at what's going on, the worst case is if we have n over x drops, and then we have to check all the remaining x minus 1 floors. Well, If the first few drops are a little bit larger, if it cracks quickly, then I haven't done N over X floors. I haven't done N over X drops. So if it's going to break early, this number is not going to be as large as N over X. So what you can do is you can actually have it a little bit larger in the beginning and then get smaller and smaller and smaller. So that what you can do is you can equalize. So what you would want to do is say, if you crack after one drop, it would be 1 plus X minus 1 drops total. If you crack after 2 drops, you want that to be 1 plus, and so there's going to be 2 plus, now what would you have over here? You would want to have X minus 2 drops. You want it to be the same number of drops each time. So you want to be dynamically adjusting. So I will leave it as a hint. Anybody know what these numbers are? So these are the triangle numbers. So if you use triangle numbers, you can actually do a little bit better. Now, one of the big themes is always general ones. What would we do next? So given our success with 2 eggs, what would you try? Sorry? You could try n eggs, but b times be 3. 3 eggs. So now, let's say we go up by X each time. Go up by X. So what's the worst case? Worst case, we have N over X drops before the first one breaks, right? And then we have X floors, what's X minus 1, who cares, with 2 eggs, right? How many drops does it take to do X floors with 2 eggs? We said the number of drops is N over X plus X, where X is going to be square root of N. So for us, G of square root of N is basically 2 root N. So if we have N floors and 2 eggs, the best is going to be roughly 2 square root of N drops. So over here, this should be N over X plus 2 square root of X. Right? So we want to minimize this. So one approach is N over X equals 2 square root of X. Therefore, N over 2 equals X to the 3 halves. So X is going to be on the order of some constant times N to the 2/3. Or we could use calculus, and we would get critical point 0 is equal to, the first one is going to be negative N over X squared plus the 2 and the 1/2 cancels, and we get X to the minus a half. So that implies N equals X to the 3 halves. So that gives us X equals N to the 2/3. So this would give us N equals X to the 3 halves. So X equals N to the 2/3. So we were missing a constant. So this idea of equating the two is not going to work perfectly, but it's going to give the correct order of magnitude with N. So now, when we have number of eggs, X is a function of N. With 2 eggs, we had something like N to the 1/2. With 3 eggs, we had N to the 2/3. What would you guess if we had little n eggs? What would you? It seems like a very natural thing to conjecture. Right? But you can try this. We now just did what's going on with 3 eggs. You can now do 4 eggs and say, let's do 4 eggs where after the first one breaks, now we have 3 eggs left. And maybe you can prove something like this by induction, or just prove it directly. So at this point, what we've done is we've just done a pure math problem. We've come up with what's the best strategy. And the entire strategy is based on worst case analysis. We are trying to minimize the worst thing that could happen to us. So how many people have done economics? Have you seen a principle like this in economics? You know, minimizing the worst possible outcome. Okay. This is, in many things in life, a natural strategy is to try to minimize the worst thing that can happen to you. What's another strategy? Maximize the best thing that can happen to you. And of course, if you're trying to maximize the best thing that can happen to you, you open yourself up to something really bad. So a lot of this depends on how risk averse I am. And there are many situations where people are not willing to do what is in their best interest overall because the effect of failing is so catastrophic. So I am a huge fan of Bill Belichick. One of the things I love about him is he has enough years of success that he can, well, if he actually felt like talking to the press, he could actually tell them what they could do with themselves. He can actually make decisions based on what he thinks is right without worrying so much about the pushback. There's a lot of analysis that's been done that, you know, decisions being made in sports and business and whatnot are often made to protect your ass because they're defensible wrong decisions if they don't work out, than to take a risk where if it works, you know, it's wonderful, but if it doesn't, it's your neck that's exposed. You know, a great example in football is going on 4th down. Teams don't do it nearly enough. And there was a great game years ago, Patriots versus the Colts, where the Patriots went on 4th down. And if they had made it, they would have won the game. They could have run out the clock. They didn't. Colts got the ball back. They gave Manning a short field, drove down, scored the winning touchdown, and the Patriots lost. And he had a very verbose for him press conference where when he was asked, he said, I did that because I thought it maximized our chances for winning next. And you know, they eventually showed the computer simulations which showed he did increase the chance of winning the game by a couple of percentage points by going for it on 4th down. It was the right decision. But a lot of people don't have the stones, you know, to go for it in, you know, a case like that. Because if it doesn't go well, you know, if you're young, it's very hard to survive something like that. So the question in a problem like this is, what should your strategy be? Are you trying to minimize the worst case scenario, minimize the maximum number of drops you will need before you determine it, in such a way that we're still safe and we still know that we will be able to find the bad floor? Or do we want to try to maybe minimize the expected number of drops and say, you know, there will be some times we're going to have a really bad run. But there'll be other times when we'll save so much, you know, if you're going to be playing this game many times, that the savings we get from those few times will more than make up for those times when we really fail, if you have a large enough bankroll to survive those bad losses in the beginning. And again, you know, think about, you know, the decisions being made about the pandemic. You know, people are, for the most part, I think, operating under good faith, good assumptions, trying to read the studies. But the problem is so many people are so afraid of, what if we have things wrong? You know, what are the consequences? And so, you know, speaking to a mass audience right now, you can think about the choices that people are being, you know, forced to make. And, you know, what are we trying to maximize? And when you look at some other school districts as to what they've done, and the fact that a lot of schools last year did not have in-person classes at all, you know, we had in-person classes. What is an acceptable level of risk? And how do you determine that? So when you're trying to use probability, these are things I really want you to think about. All right, this is a good place to stop for today.